The objective of this project is to perform a modal analysis of a cantilever beam by analytical and experimental means. First, we will start with a brief theoretical derivation of the equation of motion, followed by the experimental procedure and results. Concluding this project is a comparison between the theoretical prediction and experimental results. Consider the free body diagram of an infinitesimal piece of the shown beam. The force and moment balance can be derived. Substituting equation 1 into equation 2 and assuming elastic deformation, it can be shown that the governing equation of the beam is given by the following. For a free vibration beam, the equation of motion simplifies to the following. To determine the natural frequencies and mode shapes, we assume a separable solution of x and t, which simplifies the equation of motion to equation 5, where beta is given by the following. A general solution of equation 5 takes the following form. Applying the appropriate boundary conditions results in the following eigenvalue problem. To find a non-trivial solution of beta, the determinant is set to 0. Numerically solving for beta results in the following solutions of the natural frequencies, where beta is given by the following. The mode shapes corresponding to these natural frequencies can be found by, for a specimen of the following specifications, the first three natural frequencies will be 13.9, 87.2, and 244.1 Hertz. The mode shape of these three natural frequencies are shown. It is noticed from the second and third modes that there are points that don't change with time, which are represented in red. These points are called nodes. The second mode has one node, while the third mode has two nodes. The experimental setup consists of a shaker, an accelerometer, a signal conditioner, a signal generator and analyzer, a magnifier, a compressor, and a vibrometer, which is not shown in the diagram. In this experiment, we extract the first three natural frequencies of the system through determining the frequency response function. The signal from the accelerometer that measures the deflection of the beam at the free end is transferred through a signal conditioner to the signal analyzer. The test is done between 9 Hz to 350 Hz, and the peaks at which resonance occurred were around 13, 82, and 240 Hz. This agrees reasonably to the theoretically obtained results from the analytical solution. We also show here the corresponding bending deformation of the elastic beam at different driving frequencies. The second part of the experimental verification is finding the mode shapes by exciting the beam at its first three natural frequencies. This is done using an electrodynamic shaker that is driven using an air compressor. The signal generator outputs a signal to the magnifier, which then outputs it to the compressor. To measure the transverse deflection across the structure, a laser Doppler vibrometer with scanning capabilities has been used. The measurement procedure starts with identifying the points of interest, which are presented as white or black dots. Once prompted, the scanner head starts to measure the velocity at these points and categorize them in mainly three categories: optimal, which is the light blue, valid, which is the dark blue, and invalid, which is the red. Once it is done from the first scan, the scanner repeats the measurement at the non-optimal points to achieve optimality. Finally, the following is a comparison between the experimental and theoretical findings. It is seen that our findings reasonably agree with the theory. These discrepancies may be attributed to errors in actual parameters, such as modulus of elasticity and dimension measurements. Furthermore, the tested specimen has a lower length-to-width aspect ratio, which causes it to act more like a plate. This is seen in the frequency response function, as one mode at 140 Hz due to twisting was noticed. In general, however, the modes agree to a great extent with the theoretical predictions.